Started?
Yeah, okay.
That one should have plenty of memory. Okay. So, any other questions besides the video? Okay. So, we're going to put this, I'm going to put a pulley right in here. All right, now, we've dealt with pulleys before. What does the pulley do?
Reduces force needed to pull, but increases distance.
Well, it reduces force if it's on the bottom. This is going to be on the top here. So the pulley merely allows me to do what?
Change direction.
Change direction. So now if I apply this force F here, how does that change my free body diagram?
Because gravity actually is not equal to the force of normal, it's adding on to your normal force. No? No.
For this guy, the free body diagram is exactly the same. Just the only difference is now instead of pulling out, I get to pull down. Okay? Which isn't really much of an advantage, but now I can pull any direction I wanted to. So now I'm going to change it up. Instead of me pulling with some force, I'm going to pull with this mass here. Okay, now I need to distinguish the two masses. So since this guy was here first, I'll call him mass 1. And very creatively, I'm going to call this mass 2. Okay. Now, since I can use this mass to pull it down, what's going to happen here is that my force is no longer going to be 5 newtons. It'll be related to what?
So how fast that's going down.
Yeah. So what's going to happen here is that it turns out that this block will always accelerate this guy regardless of their differences in masses. For simplicity, we're going to pretend like this guy is heavier than this guy. Does that make sense? But without friction, even if this guy was lighter, it would still go this way because these two forces would cancel. Does that make sense? If there's no friction. And in reality, is there no friction? Not most of the time in real life. But, so just for simplicity's sake, we're going to make M2 bigger. So I need a mass for M2 that's bigger than 30 than M1. Okay? So this mass is 30 kilograms. Okay? So let's look at the free body diagram for this guy. What forces are acting on this mass right here?
Gravity. And tension.
Is this force of gravity bigger than this guy or smaller?
Same.
Oh,
Bigger.
Bigger.
This is going to have a bigger force of gravity than that guy because it's a bigger mass, right? Now, this guy is bigger. So here, let me label all this. This is all mass 1, whatever. Okay. So, that's the force of gravity pulling down. We all agree with that. Is there any other forces?
Tension.
Tension caused by the rope, which is in what direction? Is it bigger, smaller, or the same size as gravity?
Smaller.
Why do you think it's smaller?
Because it's moving down.
Because it's moving down. Does everyone see that? I'll call this force of tension. This one has to be smaller than that because if they were the same size, it wouldn't move. You okay there? How is this stuff related to back over here? What force is pulling the box?
Gravity.
What's pulling the box?
Oh, the
Forget
other
about
mass.
this. Just look at this.
The
What's
other-
pulling the box?
The rope.
The rope. So this force here that I have labeled as F, which we don't know what it is anymore, this F is actually F of T. Y'all see that? Because whatever force is in this rope has to be in that side too. All right, assuming that this pulley is pretty light, which our pulley there is. Okay? So the force of tension in this part of the rope has to be equal to the force of tension in this part of the rope. Does that make sense? Okay. So I'm going to write a net force equation just like I did here. I said F net. But it's a different net force. This is the net force on block 1. This is the net force on block 2. What forces are acting on this block?
Gravity and tension.
Gravity and tension. So in order to add them up, one of them has to be positive, one has to be negative. But I've already established a coordinate system. Okay, do y'all see my coordinate system over here? I said that direction is positive, right? So what does the pulley do to my coordinate system?
Change the direction.
Yeah, it turns it, it bends it. So which direction should be positive on this?
Down.
Down. Do y'all see that? And I'm just staying consistent with this because eventually you can think like if I pull this long enough, this thing is going to come over the pulley and come down too. All right. So when I add up my forces, I'm gonna say the force of gravity minus the force of tension. Okay? So what I need to do is I need to solve this for the acceleration of my blocks. Okay? So force is mass times acceleration, so my net force, this is mass 1 times the acceleration equals the force of tension. Okay? Can I solve this equation? I know the mass, right? Do I know the acceleration?
Yes, because we just did it.
Well, I'm looking for it. Do I know the tension of the rope? No, I have one equation with two unknowns. I need a second equation. Here it is. My net force in this block is mass 2 times A. Are these A's the same or are they different?
Same?
Same? Why are they the same?
Because they're attached to the same rope.
They're attached. Like, think about your arms and legs. They have to have the same acceleration as you because they're attached to you. If they did not have the same acceleration as you, they would not be attached to you. Make sense? So, since they're attached, they have to have the same acceleration. Force of gravity, how do I calculate the force of gravity on this guy? Close. Fg equals m times
G.
what is G?
9.8.
9.8.
Oh, 9.8.
Okay, I'm sticking to letters right now because I don't have enough numbers to plug in. And again, f of t is f of t. But so again, I know my m's, I know G, but I don't know these two. Okay, but it's the same as these two, right? So should I solve for A or should I solve for f of t? I think it's pretty easy just to solve this one for f of t because it's already done. And just plug that in here. So that's what I'm going to do. So this is from your algebra class, a system of equations. Two equations, two unknowns. You can add them together, you can substitute. I think it's just easy to substitute because that guy's already plugged in. So I'm just going to rewrite this. M2A equals M2G minus, now instead of FT I'm going to write M1A. Okay, now I know everything and I only have one unknown, right? So now I have to solve it for A. What do you have? But I've got two of them, so what do I need to do?
Cross them both out?
How do I combine them? Combine like terms, I gotta move this term over here. M1A plus M1A. So we have M2A plus M1A equals M2G. Now what do you do? Starts with F. Rhymes with raptor.
Factor.
Factor. Something. Okay. Factorize A, M2 plus M1 equals M2G. So now I do what?
Math?
Been doing math. M2 plus M1 over M2 plus M1. That'll cancel, so A equals M2G over M2 plus M1. Okay, now, I did this for two reasons. Number one, I gave you all this sheet here. You all remember this? Y'all did this last time?
Yeah.
And some of these problems on here, like number 5, asked you to find the speed of the mass when it passed through the equilibrium position. A lot of students were bothered by the fact that there were no numbers. Okay, I can solve this without numbers. As a matter of fact, most of the time it's helpful to solve without numbers, because even if I had plugged in numbers over here, do you see I can't really do anything with this number here? I can plug in 10, but I'm going to be dragging 10 along for a while. All right? But see, now that I get to this point, I can plug in my numbers. What's M2?
30,
30. What's G?
9.8,
1.8 meters per second squared. What's M2?
30.
30. What's M1?
10,
10.
What's 30 plus 10?
40,
40. So, basically it's reduced to 3/4 times 9.8. What do you get? Calculators.
don't have one.
Hold on, calculator.
That's all the way over there then.
All the way over there.
Oh my.
I'm tired.
Use your phone.
There you go.
7.35.
That's in my pocket.
7.35, okay.
Like this lazy person.
Check him.
I didn't get any sleep.
Here's the second square. Okay, so we got this number. Is this number bigger or smaller than gravity?
Smaller.
Does that make sense?
Yeah,
Why?
because we established that it was smaller than gravity.
Well, gravity, if this rope was cut here, this thing would just fall at the acceleration of gravity, right?
Yep.
But because this rope is on here, this thing has more inertia. This thing's going to sit here, and it can't go as fast because it's got to drag this other block behind it. Okay, like we've ignored friction. Okay, it's got to drag this guy behind it. Does that make sense? And whereas gravity's acting on it, it's canceled out by something else. You know with me? So this acceleration of this hanging block is going to be less than gravity. Okay? But I want you all to see this here. That the acceleration of the block really only depends on this ratio. Like, yeah, G's, you're multiplying there, but it's the ratio of these masses. Y'all see that? Okay. Are there any questions right now? How often do you think this comes up in real life? Not that often.
Well,
I mean, you can do it, but I can't think of anything off the top of my head where this is an actual thing. However, an Atwood machine is a real thing. Does anyone know where you find Atwood machines?
Cranes.
We've estimated, yeah, you can find them in cranes. Maybe Ms. Jenkins estimated that y'all probably use one of these once a month, depending on how lazy you are.
I don't know.
Elevator.
Oh.
This is an elevator. The only difference between this and an elevator is an elevator has a motor up here attached to the pulley. Because think here, right now these two have the same mass, so no matter where I put them, they'll stay there, right? But let's say that you get in the elevator here and you wish to go up. Well, for those of you who don't know what an elevator looks like, it's a box right here. But that's just part of the elevator. You know, there's all sorts of stuff inside the wall. And if you've ever gotten a chance to look at one of those glass elevators, you can watch, there's a counterweight in the wall that will do the opposite of what the elevator does, right? And these two things are going to be close in mass, but they won't be the same. Because sometimes you get in the elevator and the elevator will be heavier, or when there's nobody in there, the elevator will be lighter, right? And so you have this motor that can turn back and forth, and it doesn't have to use much power because they're close in weight, okay? Now, how many of y'all have seen inside the elevator where it says, do not exceed like 2,000 pounds or whatever?
Yeah.
What does that mean?
Counterweights.
What happened? What do you think is going to happen if you exceed 2,000 pounds? You'll all die. The ropes will break and you just fall down. Well, basically,
The motor can't turn.
yeah, it's based on the power of the motor, and the more powerful the motor, the better it can compensate for differences in its weight, right? So ones that have weak motors tend to have a low weight there. Ones that have high motors or powerful motors will have a larger weight that they can move. Now, I'm not saying that you should go ahead and exceed the weight and see what happens, but you won't die. At worst, it probably just can't move, okay? The chances are it'll start trying to move, then you get stuck between floors, and that's not good for anybody, right?
Well,
So you have to shove someone out?
All right, but I want y'all to see here that this wasn't, I think this was really easy. This wasn't too bad, and now you're like, algebra, okay? So what we're going to do here is we're going to switch this from being like this to being an Atwood machine, okay? Now, I want y'all to see this isn't that different, okay? So I'm going to change this, all right? We're no longer on a flat horizontal surface. Now we're going to have mass 1 be over here. Make my pulley bigger. Okay, that totally is sitting there. Okay, so again, we're going to assume that mass 2 is bigger, so it will accelerate in that direction. Now in this case, if mass 1 is bigger, is mass 2 going to go down?
No.
No, not unless you have something else adding to it. Okay, so is this free body diagram still okay
no.
for this?
No.
No. Is the force of gravity the same?
Yes.
Yeah. But tension no longer points that way. What direction does tension point?
Oh,
Up. Now, in this case, the force of tension was smaller than the force of gravity. Is this force of tension going to be bigger or smaller than gravity?
Bigger. Bigger.
If it's the same, will it move?
No.
No, so it has to be what?
Bigger.
Bigger. And again, the force of tension here should be the same as the force of tension there. Y'all with me? Now again, if we've established this direction as positive, you'll see that positive is what direction on this?
oh,
Up. Y'all see that? It's just bending our coordinate system. So this is positive and this is negative. So we'll go ahead. Does anything over here change for mass 2?
Sorry.
no,
No, this is all exactly the same. But if we come over here to mass 1, the net force is the force of tension. Is that it? Is that my only force acting on it? Oh, now I've taken into account what? Gravity. Why didn't I have to take into account gravity before?
because it was on something.
Because it was canceled by the normal force. Good, both of you.
Thank you.
So we have mass 1 times gravity here. So just like I wrote mass 2 times gravity there. So now I've got an additional term here. Y'all see that? But again, I still have 2 equations with 2 unknowns. Again, last time I solved for the force of tension. Do y'all want me to do that again? Give me the same method?
Yeah,
Okay. So I'll add this to both sides. M1G plus M1G equals the force of tension equals M1A plus M1G. Everybody okay there? So now I'll take this thing and I'll substitute it up here. So I'll make my changes in green. I'm going to pick this guy up and put him over here so we'll look at it later. So A is M2G over M1 plus M2. Okay? So before, I started with this, and I substituted in what? Just MA. Now I have to substitute in both these. Hang on, we're almost done. I know it's more. M1A plus M1G. Everybody okay there?
Yeah.
What do I have to do with this negative?
Add it on the other side.
Distribute.
Or maybe not.
M2A equals M2G minus M1A minus M2. No, still M1. G. Now, just like last time, I have to move this A over to the other side. Cancels, so I get M2 plus M1. We're going to go ahead and do what to it?
Didn't take out the A.
Take out the A, factor out the A.
Or background, whatever.
But over here, I'm left with M2G minus M1G. What can I do there? I can factor out the G, just like I factored out the A. Y'all see that? I didn't have to do that last time because there was no second term here. Okay, but again, I'm going to divide by M2 plus M1. And that's the guy we're after, right there. So A equals G times M2 minus M1 over M2 plus M1. Okay, I highly recommend that you memorize this equation. Okay, because Atwood machines come up quite frequently on the AP exam. And I don't think this was hard. I don't think this was hard. You might get tripped up in the algebra here if you haven't been practicing your algebra. But I don't think this was hard, okay? But the thing is this took some time, right? On the AP exam, the one thing that you're going to be pushed for every single time is time. So anything you can do to save time is worth it. So I highly recommend memorizing this equation. And all this is it says the acceleration of this system is equal to G, which is constant, times the difference in the masses over the sum in the masses. Okay? So if the masses are exactly the same, let's say, what is this? 100 grams. What's 100 grams plus 100 grams?
200.
200 grams. What's 100 grams minus 100 grams? 0. What's 0 divided by 100? Or 0 divided by 200? 0 times g.
0.
What's the acceleration of the system?
0.
0. But if there's a slight difference, this is 2 grams. Okay? What is, I'm going to put it on one of them. What's 102 minus 100?
2.
I'll get 2 over, what's 102 plus 100?
200.
What's that reduced to? 1 over 101?
Times 9.8.
Oh, that's a small number.
But I'm multiplying this times g, and g is about 10. That's about 100. So,
It's still a small number.
what's 10 over 100? This is going to reduce it to what? 1/10 meter per second squared. So, a nice thing this has when we're dealing with just science is I can use this machine to measure gravity. Because again, with gravity, if I put something at the ceiling in here, it takes less than a second to fall all the way to the floor. And what's the one big problem with anything that we've done in this lab this year? Accurate timing. And we've established that y'all suck at it, right?
Thank you.
There you go.
Hey, it's human, right? But the thing is because you have a reaction time, let's say your reaction time is only 1/10 of a second. Well, it only takes 4/10 of a second for an object to fall from the ceiling to the floor in here. If your reaction time is 1/10 of a second, you could be off by almost a quarter of the time. Does that make sense? So that can lead to huge errors. But if we can reduce that, we can make it move much slower than before. Y'all see that? So, how different is this equation from this equation? Here we have the sum, but did we have a difference up here? No, there's no difference because we didn't have to worry about gravity because it was sitting on a table. But do y'all see that even with this thing, it's not really that different than this? In this case, you don't have to worry about M1 because gravity didn't affect it. Or it does, but it's canceled out. So, let's talk about your lab today.